Here is the first of some elementary results associated with the normal distribution. Here is the theorem. If x has the normal distribution with parameters mu and sigma squared, then the random variable y, which is ax plus b, will be normally distributed with mean a mu plus b and variance a squared sigma squared. In other words, the ax plus b applies directly to the mean, and then for the variance the shift is ignored, which we've seen before, and the parameter a comes out squared in the variance, and that's because variance is a quadratic operator. The proof of this will use the moment generating function, and on the previous slide we derived the moment generating function of x as mx of t. Notice it has a subscript now because there's both an x and a y in this particular result, and it is the expected value of e to the tx, and again on the previous slide we had that as e to the mu t plus 1/2 sigma squared t squared for any t between negative infinity and infinity. So the purpose here is to find the moment generating function of y, which is ax plus b, and that will be my of t is the expected value of e to the ty, but we know that y is ax plus b, so this becomes e to the t ax plus b, and when you take that t and distribute it across to ax plus b, you get the expected value of e to the atx plus bt. Now, using like base add exponents but in reverse, this is the expected value of e to the bt multiplied by e to the atx, and the e to the bt does not contain any capital X values, so it is a constant in this expected value, and constants can come out front. So there it is e to the bt multiplied by the expected value of e to the atx. Now, when you're calculating the expected value of e to the atx, you go up here and say, if I replaced t in this particular expression up here by at, what would happen? Well, I'd get e to the mu at up here, and I would get 1/2 sigma squared times at, the quantity squared, and that's what you get right here. Finally, the next step, if you combine these terms, namely get all of the terms that have just t in them, you'll get e to the a mu plus b times t plus 1/2 a sigma squared, that's what occurs right here, multiplied by t squared. Now at this point it becomes a pattern matching problem, and that is you look at what you know the distribution of a normal is, and it's got that particular form right there, but instead of having a mu here, notice we have a mu plus b. So we're going to have a normal distribution, and it will have a mu plus b as its mean. And in addition, there is a 1/2 sigma squared t squared. Well, this will be 1/2, and here is sigma squared, so you're going to have a variance of a squared sigma squared here. And this has the moment generating function for a normal random variable. It has this as a mean, this as a variance, and that is exactly what we have up here as a result, and that completes the proof of the theorem.